Okay, so welcome again. So this time we are going to have additional examples on thermal stress. So I have adapted or I'm going to present to you a problem came from the book of Hibbeler. So this is a problem 269. So as we can see in the figure, the platform is being supported by these three rods here, copper, aluminum, and another copper. So the central rod here has a gap on the platform. Okay, so there is a gap on the platform, space between there, and then an initial temperature is 10 degrees, and then eventually it will increase to 95 degrees Celsius, and then the properties are given. We are tasked to determine the stresses after a change in temperature from 10 degrees Celsius to 95 degrees Celsius. So as a solution, we need to determine what is the final behavior of these three rods if there will be a change in temperature. So what we do is to compare first the coefficient of thermal expansion. As we have been saying that there is a difference on the properties according to the material, of course we need to look into that. Okay, so in this given, let us compare the property of copper versus the aluminum. So I'll just write its corresponding alpha. So the alpha for copper is equivalent to 16.8 times 10 raised to negative 6. This is meter per degrees Celsius. So we have a prefix here of micro. So that is multiplied by times 10 raised to negative 6 to be consistent, to have a consistent unit of meter paired to its denominator. So for the aluminum bar, we have 23.1 times 10 raised to negative 6. So between the two, copper and aluminum, it is obvious that aluminum has a greater coefficient of thermal expansion, which implies that it will have a more length to be expanded compared to that of the copper. And if there is a temperature drop, it will also have a greater length that is to be contracted versus that of the copper, because we have a greater value. 23.1 times 10 is negative 6 is greater than 16.8. So knowing that, we can verify that by computation of our deformation due to temperature. So I'll be using here a variable, okay, delta due to temperature if the involved stress is thermal or temperature change, and then I'll maintain our variable, which is usually denoted by deformation, whenever there is a compressive or a tensile stress. So with this, let us now compute for the deformation. So we'll just compute the deformation caused by temperature change or thermal stress. on the premises of the initial temperature increasing to 95 degrees Celsius. Okay, so 95 degrees Celsius is the final temperature and this is the initial temperature. So we can compute now for the corresponding deformation on that premises. So for aluminum, let us have delta T, or deformation due to temperature of aluminum. Okay, so we can see here T is now indicated. This is equal to alpha L delta T of our aluminum. And then we simply substitute the given. We have 23.1 times 10 raised to negative 6 multiplied by the original length, which is 750, and then the delta T is 95 less 10. Okay, so delta due to temperature of the aluminum is equal to, we have 1.47 millimeters. Okay, so similarly, we are going to apply this deformation due to temperature this time for the copper. We have alpha L delta T for the copper rod. So we're gonna have 16.8 times 10 raised to negative 6 times 750, the same, and then the same change in temperature. So we have delta T of the copper will be equal to 1.07 millimeters. Okay, now that we have these values, we can now proceed to illustrate what is the final position of the platform if both material will extend according to the thermal stress. Okay, so here I'm going to draw our final position. Say this is the final position and this is the original position. So this is the initial position. So let us indicate the rods here. So these are the external rods placed. By the way, this is a copper, and then the aluminum is placed internally, or this is the central rod. Okay, so let us have an illustration indicating now our dimension. So let us zoom that out. Okay, so here, of course, the gap is already given. So this is 0.18 millimeters according to the problem. Okay, so we will now extend these three bars according to what we have computed. So first, the aluminum will extend to 1.47 millimeters. Okay. It will extend to 1.47 millimeters. See, this is the elongation of that rod. Okay, so I am gonna label this as delta T of the aluminum, which was computed to be equal to 1.47. So this outer rod will also extend, but we must have to investigate the dimension, whether these outer rods will exceed the level of the aluminum, or it will not reach the level of that top of the aluminum. So how shall we investigate that one? Of course, we have already the value of the extension due to temperature of the copper, 1.07. And of course, for this being 1.47 mm, we can now determine the remaining dimension here. Okay? Because we need to have a common reference to determine whether your copper will exceed the aluminum or will it be shorter than this extension. Okay? So 1.47 less 0.18, that is 1.29 mm. Now, if this is 1.29 millimeters, therefore, the extension of the copper rod will be shorter than 1.29 because our calculation is just equal to 1.07. So this is now the delta of the copper, the delta of temperature due to temperature of the copper rod, which was computed to be 1.07. So our criteria that this is shorter, we'll just compare it to 1.29. Okay, our reference is 1.29 so that we can identify or locate properly the level of delta T of the copper rod. And we found out that it is still shorter than that of the extension of the aluminum. So if that is the case, our next question is that what is the meaning of this elongation? Because the copper here is originally attached to the system or attached to the platform. So to illustrate that, if this is the platform, remember that our copper rod are actually attached to that. Okay? Though the central rod is having a gap. So if this is the case, therefore, we compare now the relationship or the effect of the aluminum rod to the platform. So we will have, what is the aluminum effect? What is the effect of the aluminum rod to the platform? Okay, so that is the question. So as we can see, the extension is much greater than delta t. Therefore, this platform is locked on the aluminum rod, meaning it is restraining this to go up. However, this aluminum tends to push our platform here. Okay? So the answer is the aluminum is pushing the platform upwards. So if there is a push between the aluminum rod and the platform, therefore, the stress in the aluminum rod will be a compressive stress. Okay. So why is it pushing that one? Because, again, these two outer rods are actually attached to the platform. So therefore, if this tends to extend beyond the thermal expansion of copper, therefore it will begin to push it upwards. Okay? So that is clear, no? For the next question, what is the effect of the platform to the copper rod? Okay, so with the platform tends going up because of the push of the central aluminum, while this is going up, okay, because of the push of this. Therefore, the answer is the platform stretches the aluminum rod. So therefore, the type of stress on the aluminum rod should be tensile stress. Okay. So, we can now place the platform on that premises and assumption. Okay. So, I'll just have to bring this down. Okay. So it is not exactly at the level of the aluminum, but the aluminum will come in to the rod, and that this inserted, or this portion that is bounded by this platform, let me shade that one. This is the fiber which is subjected to compressive stress. Okay, so this is the subject for compressive stress. So if we're going to label that This now is delta of aluminum. Now, this time, there is no subscript of T because this is no longer caused by temperature, but it is caused by a push by the aluminum. That is why this is a deformation due to axial loading between the platform and the rod. Okay? So that is denoted by delta AL. So again, there is no subscript of T here. Subscript of T intends for the temperature expansion. Okay. So now for the copper, remember that copper is attached, right? And we have just said, and we found out that because of the aluminum pushing this up, and this copper is attached to the platform, when the platform goes up because of the push, of course, susunod yung copper, and it will elongate to the action, to the direction of the action of the platform. That is why we are going to have a line that extend to the platform since this is actually attached to it. Okay? And shade that one. And this portion now is a stretch due to push or pulling the copper upwards. Okay? So with that, we can indicate this dimension to be delta of copper. Okay? Now that we have established all the dimensions needed, remember that that most problems in our subject relies on the three equilibrium equation and the geometry as well. So when we talk of the geometry, just think of dimension and angle on the figure. Okay, to have a relationship between the formation of the members. So in this case, the direction of our action is only upwards. So we will just have to apply a dimensional relationship between those deformation. So let us try to redraw our illustration. Okay? So say this is the platform initially. Say this is the platform after. Okay? This is the central rod, aluminum. And these are the outer rods placed. Remember that the measure of the level of these two rods is at this line. Okay, anyway, let us label that. This is 0.18. Okay. So we have just said that this central rod will extend up to this level, and a certain portion of the rod will be inserted on this platform. So next is we're going to label that. Okay. So this level up to that, okay, from from the top of the aluminum rod, the final position, up to the top of the initial position. Of course, this is delta T of the aluminum rod. And then, for the other rod, we're going to extend that again. So this initial extension or elongation is due to the change in temperature, wherein this is delta T of the copper. And since that is originally attached, of course, the excess here is a stretch that is caused by the push of aluminum to the platform, and as the platform goes up, it will also pull your copper upwards. Okay, so this is delta of copper due to tension. Okay, we know that. And shading this one also, this is delta of aluminum due to push. Okay, so as we can see now, we can form a relationship between those deformation. Just refer to the dimension. Okay, so when we refer to the dimension, let us have a reference line to relate these variables. So let us establish a line common to those variables. If we consider an upper line coinciding to this, that is the upper level, and we will choose this one as another level. Now this level is now common to the variables here on the left and on the center. That is why we'll just have to determine the variables involved on this level. Therefore, we can say from this, we just add that one, and this is the dimension, right? So delta Cu plus delta due to temperature of the Cu is equal to, what is the equivalent dimension from this variable on these two lines, upper level and lower level? So if we can see, we'll just have to deduct delta AL and 0.18 to the delta TAL in order to become this dimension. So if we do that, that is delta T of aluminum minus 0.18 minus delta aluminum. So this is our equation, right? So if you have a strategy, a different reference line, say I'll just copy this one. Okay, sorry. So if we have different line, because it is actually your option where to place your reference line. Okay, say your line is the green now. Say for example, if you choose to have an upper line here coinciding to the topmost fiber of the aluminum, you can also do that. Say this is the upper level, and if you choose to have this as your lower level, okay, then these two lines will now be common to these left variables and the central variables here. All we need is to determine that dimension. Okay, now determining that dimension, if we have this left portion, what is that dimension from point 1 up to point 2? Of course, we add this one plus this 2 and equate it to delta T aluminum. So we have an equation equivalent to delta Cu plus delta T Cu plus this one. Okay, this is 0.18 and this is delta of aluminum plus 0.18 plus delta aluminum, and all of this will be equal to delta T of aluminum. Okay, so if you would notice, the equation here is also the same as this, what you have derived here. Because if I'm going to transpose this to this, becomes negative. Okay, here it is. And if I'm going to transpose aluminum here, becomes also negative. So these equations are just equal. So again, your derivation is based on your strategy, how to relate the dimension from one side to another or from one material to another. So it depends upon you. So wherever you're gonna place the lower level and the upper level, it is up to you. But what is important here is the level you're gonna choose is there is a dimension on it, because you cannot place a level here because you do not have any distance here, or you cannot just place anywhere, but we'll just have a level that is having a dimension. Okay, so that's it. So if I'm going to adopt this equation, so adapting this equation, or you can adopt any of those equations, so but this, I'll just adopt this one. So we have to write the equation according to this adapted equation here. We write the formulas. Delta Cu is axial deformation. Of course, this is PL over AE of the copper. And we have already solved for this deformation due to temperature of the copper. And this was computed to be 1.07. And then this is a deformation due to temperature of the aluminum. So I believe this is 1.47. So we're going to deduct 0.18 there. Okay. And then minus PL over AE of the aluminum. Okay, so let us refer to the given here. Of course, this is P of Cu. Okay, the length of the copper here is 750 millimeters, and the area for the copper according to the problem is 500, having 120,000 megapascals elasticity. Okay, 500, and this is 120,000 plus 1.07 is equal to 1.47 less 0.18 minus P of aluminum. So aluminum is 0.18 shorter than that of the copper. So that is 70 or 750 less 0.18. The area, we refer to the problem. We have aluminum 470,000 megapascals. So area is 400 and E is 70,000 megapascals. So as we can see now, we cannot proceed further because there are two unknowns here, so that we will have another equation in order to supplement this first equation. So what did I tell you a while ago? We are solving by utilizing the three equilibrium equations and then supplement it by the elastic deformation. So from the elastic deformation, we come up with this equation, and now we are going to refer to the free body diagram for our equilibrium equation, or the forces, or the external forces. So having said that, let us note that in the problem, we neglect the mass of the slab. So if we are going to illustrate the slab here, which is supposed to have a weight on the center of gravity, of course, this W is no longer, or the mass is no longer considered, because according to the problem, let us neglect that one, or neglect the mass of the slab. So what is left are the forces by the aluminum, and we all know that the aluminum is pushing upwards this slab, and a compressive one, say this is P of aluminum, and as an effect, the platform is pulling the fixed connection between the copper rods on the external rod columns. Okay, say this is P of the copper and another P of the copper. Okay, so we have actually established that aluminum tends to push this upwards, and as the copper is fixed and attached to the slab, as this slab goes up, of course there will be a resistance on the copper, and that is a tensile reaction. Okay, so with this, we can now say by summation forces vertical is equal to 0, we have two downwards PCU that is indicated by negative, and an upwards aluminum, this is equal to 0. So simply, P aluminum is twice PCU. Say this is the second equation. That is to supplement the first equation. Now, we go back to this working equation, okay, by injecting equation number 2. Okay, so doing that, we have PCU, just copy that one, 750 all over 500, 120,000, alright, plus 1.07 is equal to 1.47 minus 0.18 minus, we replace P aluminum by this relationship, we have 2 of PCU, twice PCU, 750 minus 0.18 divided by 400 by 70,000. So as we notice now, there is only a single variable, that is PCU. Okay, so computing for PCU, we have 3,330.38. This is in Newton. So therefore, the aluminum is equal to twice this value, 3330.38. This is equal to 6,660.76 newtons. So finally, for the stresses, no problem because we already know the forces. We just apply this formula. Sigma is equal to P over E. Say for copper, sigma for copper is equal to 3,330.38 divided by the area of copper, which is 500. Okay, 500. And for aluminum, we have 6,660.76 all over its area, which is 400. So we have 16.65 megapascals for aluminum, and for the copper, we have 6.66 megapascals. Okay, so again, I would like to reiterate that the most important in any problem on thermal stress is to establish first the final position, because the final position we can derive a geometric relationship between the deformation, and that will be supplemented by the external forces by using the equilibrium equation, summation forces vertical, horizontal, or summation moments, equating it to 0. So with this, I hope you have absorbed what I have discussed today, and again, please try to solve problems involving thermal stresses. So there are a lot of problems in the book you may wanted to practice. And so long and good day. Thank you.